Hi and welcome to the quick summary of our most recent work presented at the BMT 2022 in Innsbruck, Austria, in which we tried to reduce the annotation effort in image segmentation by using a neural network. This work is done by my supervisor, Markus Reische, my dear colleague, Marcel Schilling, and of course me, Luca Rettenberger. First of all, why do we even want to reduce the annotation effort in image segmentation? Well, generating data sets for machine learning is quite burdensome and exhausting. If any of you listening ever worked with machine learning, you probably know that the data sets are the most crucial part and most of the time also the most burdensome and exhausting part. Particularly if you want to generate segmentation masks, this can be a big problem. You can see here on the bottom left someone annotating a segmentation dataset, and like you can imagine, this can take quite a lot of time and is not something anybody really wants to do. On the right you can see a generated segmentation mask. In that case, cell nuclei were segmented. And this big annotation effort is in direct conflict with deep learning, since deep learning usually needs vast amounts of data, and since generating it is quite exhausting, this often is a big problem. And if we now go even deeper into biomedical engineering, which is like the field which we work in, it is even worse, since in biomedical engineering you often need domain expert to label your data, and the time of those experts is often very scarce. Well, since this type of work is very important, there of course also already exists some approaches. One approach is to require causal segmentations. What does that mean? Well, if you look at the bottom left image, this is a summary of the approach which is called ScribbleSub. And in ScribbleSub, the approach is to not require full segmentation masks for annotation. So in that case, you just scribble roughly around the dog, then you scribble roughly around the cat, and then you mark the background with also just a thin line. And that then is everything the network gets to generate full segmentation masks. You have to keep in mind that generating such full segmentation masks is still the goal, even with those approaches. Another similar approach is called BoxSub, which you can see here in the center, and in that case we just require boxes instead of lines, but is a very similar approach. Those approaches can work quite well, but they do have one big problem, and that is the applicability is very limited, since you generate, if you use those frameworks, you generate not full segmentation masks, and they're not universally applicable, since such scribbles on images are not what we traditionally would call segmentation masks. So if you don't use the ScribbleSub framework, you won't be able to use those annotations. Another type of approach is to extend the learning rules for the segmentation network. We can see a quick summary overview of such an approach here on the bottom right, and we can see that those extended learning rules tend to be very complicated. This is not a big deal if you have many samples, but like I already said, in biomedical engineering this is often not the case, so annotations are very valuable. And since those extended learning rules are like extended, they do have more parameters than the traditional segmentation networks, which also means you will need longer training and more labeled samples to work with those. So those are usually not an option as well. But fear not, our bootstrapping framework is here for rescue in that case. Our bootstrapping framework requires minimal human interaction and no additional steps. Well, how does it work? We have the quick summary here on the bottom, and we can see that we do have an unlabeled dataset DU, which can be any dataset. In our case, it's some cells on the images, And then we plug this data set into a simple thresholding method. This thresholding method can be any process which does not require any labels or annotations, but in our case, those are just simple thresholding methods. And thresholding methods work like very simply, they just take the intensity values if we have a grayscale image and look for a threshold to set. So they say if the value of an individual pixel in an image is above a certain threshold, it is considered the foreground, and if it's below that, it's considered background. And that's how they work. They don't need any annotations, but they do generate annotations. Well, but we can see if we now look at those generated labels LT, that those are quite imperfect. For example, the upper left image is, well, simply a false label. It's not segmenting the cells, which is in that case the goal in this data set. But the other annotations do seem to be okay-ish. Well, they're not perfect, but they're all right. They capture the quintessence, the thing we want to tell the network about the data set. And those generated labels, they're quite imperfect. They can be very, very bad, but they are plugged into a neural network N, which can be any ordinary neural network. And we train the neural network with the dataset du and those imperfect generated labels LT. And now the magic happens in that case, since the neural network N will usually, and we've conducted several experiments which show that, will usually generate better annotations than those provided by training. Well, that is most probably the case, since the neural network is capable of learning like relations and has the freedom to explore a bit more than just simple thresholding, since simple thresholding just can't capture relationships, and in the images it's not possible. It's just a thresholding value. But the neural network can, and with those simple labels we can tell the neural network what the desired behavior for images is. And like that we can generate good labels, pretty good annotations, without needing any intervention by a human. And those labels then can be plugged into any other task you want, or as a pre-annotation tool. And now we have conducted some experiments, and in our work, the naive method T, where on the one hand Otsu thresholding and on the other hand it was k-mean clustering, and the neural network N was the unit network. For the data sets, we used two. On the one hand, we used the droplet microarray dataset, which is a screening of tumor spheroids on droplet microarrays, and we used the ISIC melanoma dataset, which are images of melanoma on the skin, which are then segmented. And the results show that Otsu and k-means produce erroneous annotations. So we can see here on the bottom, the green box, the green annotations are the ground truth. So those are the annotations which are actually provided by human labeling, but for our network we just ignored them that they are there, but just to have a ground truth to see how good our approach worked, we of course do have those annotations. And we can see here for the spheroid dataset, it is quite interesting, since Otsu and k-means also do segment those light reflections. You can see here in the ground truth those light reflections on the right of the samples are not part of the spheroid itself. But Otsu and k-means do see them as a part of the spheroid itself, which is wrong, of course. But if we then train the unit with the Otsu and the k-means labels, in both cases the reflections are mostly filtered out. Well, we can see here on the bottom sample for unit and Otsu in combination, it is not quite perfectly segmented out, but mostly the unit is able to capture this relation that light reflection is actually not part of the spheroid itself. Usual quite similar behavior can be seen with the ISIC melanoma dataset. Well, we can see in with our approach that the unit generalizes beyond simple annotations. So the unit is actually capable of finding relationships in the data sets by just providing some simple generated annotations. Artifacts in the images are learned and removed. So the unit is actually capable of recognizing them as random noise. And those enhanced segmentation masks, which are generated completely automatically, can either be used for direct application, so just plug an unannotated dataset into a framework and then use the trained unit just for your application where you want to use it. But even more interesting, since the samples, the annotations are most of the time not quite perfect, is to use the segmentation masks as pre-annotations and then just use them to just correct the wrong annotations by a human labeler. And we can see with our framework that using datasets without pre-annotation is pretty inefficient. So if you now have a dataset and you want to annotate it, it would be not a very smart approach to just annotate it if we do have such a framework which generates annotations which are by themselves already quite good. And to conclude, our work is that we recognize that annotation is labor intensive, and hence we provide a framework which automatically generates annotations. Our framework is easily applicable and open source and can be downloaded by you via GitHub. If you have any questions or want to collaborate with us, you can just reach me by my email address. Thank you very much.